Thank you, Adam, for the nice introduction, and thanks to everybody for your interest and welcome to join us today. I'm going to talk about my as a spectroscopist, our approach to non-uniform sampling. And the workshop has three parts. The first part is really we cover the basics from why we want to do NUS and how we do it. And then I'll talk about it briefly how SMILE works, and then followed by our research basically on application of SMILE to various projects, which I hope you're convinced that without NUS, the work is difficult to do. So let me start from something very basic. NMR signal first detected inside the NMR probe, and then followed by digitization. By that I mean, as I show in this example, that we recorded 32 data points, 1.25 millisecond per point, and Fourier transform that, we get a spectrum, right? Now for 1D, or for the direct dimension of multidimensional experiments, these data points are recorded in real time. So skipping them will not save us any time. But for the indirect dimension, every data point corresponding to one 1D experiments, which for biomolecular solution NMR typically takes about 5 to 10 seconds per experiment. And for four-dimensional NMR, we can quickly hit a million or more data points. So anything we could do to save the time is appreciated. One way of doing that is we simply cut down the number of points we wanted to acquire. For example, we acquire 16 points instead of 32. The spectrum looks broader, and so the resolution is poorer. Another way of doing it without broadening the line is that we increase the time interval for each data point. And although the spectrum is as narrow as the reference case, but the spectral window is smaller, and therefore peak outside this could fold it back into the spectrum, and could even fall on top of another peak. And peaks overlapping like this can never be resolved. And although there's other tricks in the past that has been proposed and used, but I think it's fair to say that the entire NMR community is converging to this non-uniform sampling trick, in which we just record a small subset of data points. And then, of course, as you can see here, there's a lot of sampling artifacts. And we need to clean that up, or we need to reconstruct the data points that we don't collect to hopefully get something like that. So by the way, the whole NUS thing is really a special application of this general method called compressed sensing, pioneered by these people. And according to that theory, our NMR spectrum is roughly approximately sparse, although Lorentzian line never really goes to zero, but within noise, you can consider that as sparse. And therefore, the time domain is redundant, meaning that we don't need as many measurements as a traditional approach. And therefore, we could just measure a small subset of it and still get something back like that. A brief discussion about what kind of math behind the NUS. The NUS data that we recorded over here is really the product of the fully sampled data set multiplied by a sampling schedule, which consists of either ones for the data that we sample and zero for the data we skip, okay? So the fully transformed, the spectrum with artifacts, is really the convolution of the normal spectrum and the fully transformed of the sampling schedule, which is known as PSF, point spread function, okay? So one way of one way of reconstruct the data is really if you could do deconvolution, because you know the PSF, you could get something back from here to there. Another way of looking at it is that in the conventional NMR sampling, we recorded 32 points, for example. Let's call it N. We recorded N points and fully transform that. We also get the N data points in the spectrum. So you can consider that as if we have N measurements and we also have N unknowns. So the linear equation is determined and you get a unique solution like this, okay? While for NUS, this is not the case because we only make measurements, we only make M measurements, which is smaller than the number of unknowns in the spectrum. So the situation is really the underdetermined. And what we wanted to do is to solve this undetermined equation. Since it's undetermined equation, so we have a lot of solutions for X. And the NUS spectral reconstruction is really nothing but find the best solution in X. And so because it's underdetermined, we need a more constraint to do that. And there's a lot of methods. For example, here are two, here are the two. One is that you add actual entropy term and try to maximize that. And also people use minimum L1 norm. That's because according to compressed theory, sensing theory, the best answer is really the sparsest sample, the sparsest solution. But solving for L0 norm for the sparsest solution is hard, but L1 norm is close enough to the L0 norm. And that's why we wanted to do something like that. And the first term is really try to make sure that the solution we get from X after inverse fully transform agrees with the data, was the measured data point. And this lambda is Lagrange multiplier, which we often use in physical chemistry for solving underdetermined system equations. And there's a lot of other methods that involves iteratively reconstruct either the time domain signal or clean up the artifacts from on the spectrum. So we are really newcomers to the NUS, and we started doing this, applying NUS by using other people's programs. And we quickly realized that almost every program treated NMR spectrum as image, consisting of a bunch of data points. While in the eyes of NMR spectroscopy, NMR spectrum usually is more, someone has a chat. Is this a question or what? Oh, sorry. Okay. So we like to see NMR spectrum to be consisting of a bunch of peaks, okay? And the peaks has a certain line shape, and usually we make it absorptive by phasing, and it should be Lorentzian line shape. And the nice thing about this is that every peak only needs 3 parameters, although, I mean, you have phasing information there, but for spectroscopists, if you write your pulse program well, you know the phasing accurately. So let's call that noun instead of unnoun. So we really have 3. For example, here, the peak position, which is corresponding to the frequency of this oscillating time domain signal. The other thing is that it's the line width, and that line width you can calculate R2 star, which is somehow related to the decay time constant, decay rate in this case. Okay, usually it's R2, and then there's a peak height over here, and the peak height is a function of the amplitude of each signal, and also the R2 value. So if we know all these 3 parameters, we could really completely reconstruct the time domain signal for each one of the peak. So one problem is this, is that this R2 star is not related to R2 directly. It impacted by a lot of other things. For example, how do you apply the window function to epidize the signal? And sometimes even how you choose the sampling schedule. If you weighted towards the beginning, and then with less density in the end, your peak could get a little bit broader. And so the question is, how do we really determine R2 from R2 star? Now I have to point it out that Dennis Torshaw um, was the person who initially formulated this SMILE algorithm, and he also tested it within MATLAB. And in his original algorithm, he has some sort of a correction factor, and he could do that because he has a complete knowledge for the window function and also the sampling schedule and everything. And therefore, he can come up with a reasonable correction. But if you want to use this for all kinds of data sets, all kinds of sampling schedule, and his original method is not general enough. So here's what I do. What I did was that what I decided to do is that I want to iteratively simulate the line shape. So looking at, this is a simulated curve, okay, by a bunch of input R2 value, and then we simulate it and then determine the R2 star from the line width. And the line is not completely linear, but close enough. And so initially, SMILE was just do one time simulation in the beginning, and established a lookup table. So just a bunch of data points of R2 input and R2 star that measured from simulated line shape. And then we just, whenever you get R2 star from the spectrum for a peak, you just look it up from that so-called lookup table. But later I found that this actually determined the accuracy is limited because some other factors, even peak position and peak sampling schedule, particularly if you do something like a partial component sampling, actually impacts the relationship a little bit. So right now the program is coded as such that we do two simulations. So first of all, we do actually 3 simulations. One is a one-time simulation, and then the other 2 simulations are peak specific. Every peak will do 2 small simulations. So initial simulation is just simulate the extreme data points, and then assume it's linear, and so we got a slope. So then what we could do is that assuming that slope is applicable for every R2 star value. So we could look up from the input R2 star, not input, from a parent R2 star value that we got from the spectrum, and using that slope, we calculated what is the R2 value, the real R2 value. Then we use that real R2 value as the input, re-simulate the line shape, and then ask the question, what is the R2 star? And since the 2-point simulation is not, is pretty approximate, rough, and not accurate, so the simulated R2 from this first round estimated R2 is really not the same as R2 star. So we get some value like that. So now assuming the same linearity, from there we estimate what is the next value of R2. So now the R2 becomes something like this. It's a little bit larger. Then we use that value again to simulate it. And then the simulated R2 star is getting closer to what you got from the spectrum. And so now basically you have 2 points. You got a new linearity very close to the R2 star. So basically, no matter how curved the relationship is, locally you always safe to assume it's linear. So now we assume it's linear locally, and from that linearity, we calculate again what is R2. And I didn't do that, but if you want to use this R2 value to do as an input to do simulation, I bet you get something very close to the R2 star that you got from spectrum. So basically, the whole approach is really try to keep simulating, and then in the end, you make sure that R2 you got should give back the R2 star that you started from, okay? So from there, we could do complete reconstruction of time domain signal. And here I just wrote a little bit 1D MATLAB SMILE version, 1D version of SMILE, and I just want to show you how this program really works. And before I play that, let's talk about briefly what we do. So first thing we did is that for each peak, we have 3 unknown, right? So we actually pick the 3 highest data points, which basically is the highest point and the 2 neighboring point, one downfield, one upfield. And then we solve analytically this Rowlandian line shape equation. And we got 3 parameters about the peak, which is in peak height, peak position, and apparent line width. And then we do simulation that I talked about in previous slides, and we get R2 from R2 star. And then we determine the amplitude. Because we have nu and R2, and we could again simulated the data using the unit amplitude. And with unit amplitude, you get a peak height, which is different from the experimental data, but the ratio of the simulated peak height and the experimental peak height is the amplitude of the signal in the time domain. So now we could completely really reconstruct the time domain signal. And then once we generate that, we removed it from the input data, and then we repeat the whole process. So let me explain. On the top panel, we call residual. And at the iteration 0, the residual is really the starting data we got. So the blue points are the sample data points, and the red points is the points that we decide to skip that we want to reconstruct. And this is the fully transformed of the residual, also the starting point at iteration 0. And the red star tells you what's the peak right now SMILE is going to work on. And the bottom panels are the reconstruct FID and the reconstruct data. For simplicity, in both cases, I don't have the imaginary, but I only plotted the real part. Again, the blue is the reconstructed one that also has experimental data, and the reconstructed and the experimental data, difference of them tell us how good the reconstruction is. And the red one is the reconstructed points that not sampled in the experiment, okay? So let's play that. And you'll see that you first reconstruct that and reconstruct time domain, then you move on the weak peak, and then you keep reconstructing the weak peak. And sometimes if the residual is stronger than weaker peak, the program try to reconstruct the residual first. And then this process iterating until everything is reconstructed. In this case, it's about 20 iterations. And in the end, you get something very close to what you input. This is not a noise-free data. This is actually a little bit Gaussian noise that we're editing in, but I forgot the signal to noise ratio from there to there. So this hopefully give you a brief idea of how it works. So now I'd like to move on to talk about the application of NUS to some of the projects that we really need high resolution to collect the data. The first one was done a long time ago by John Ho Lee, a postdoc at the time, who's now running his own show at Seoul National University in Korea. At that point, he want to estimate what is the positive phi angle propensity in disordered proteins. And he used alpha-synuclein for that. It's intrinsically disordered protein that we have been studying for a long time. So as you know, H-alpha, HN coupling is the one that we often use for determining the phi angle. And the coupling follows the Kaplan's equation about the phi angle. But it's not very sensitive to the positive phi angle. However, the C prime of the preceding residue and the H alpha of I residue, I minus 1 I residue, that J3-bond J coupling is complementary to the HN, H alpha angle, and it's more sensitive. Tell us more about the positive phi angle. And so we want to measure that, and the same thing here, we get another coupling of HN and the next residue C prime. And we also get a 2-bond coupling, which is really from here to this C prime. This is not very useful, but it's a byproduct of this experiment. The actual pulse sequence is very complicated, so bear with me for not bringing that up. You could look at the paper about that if you are interested. But then let me just highlight some of the important things about that experiment. First of all, we run this as a 4D to correlate H alpha, C alpha, amide nitrogen, and amide proton. Okay, and the coupling, as you can imagine, is very small. It's about 3 Hertz, and this is even smaller for this. So it's a small coupling, and so as you can see, we cannot really directly measure it by splitting, because this coupling is so small that line width is larger than splitting. So we use a trick called E-cozy. For those of you who know, the E-cozy trick really allows us to separate a small coupling in another orthogonal dimension that's separated by larger coupling. So for example, in this case, H alpha C prime, the small coupling is very small, and if you project the 2 peaks onto the H alpha direction, the dimension, you're not going to get splitting, okay? Because it's so small, line width is larger. However, if you separate it in the nitrogen dimension, which is orthogonal to proton, and that coupling is about 15 Hertz, and it's larger, and we can use the 4D to resolve that, and we could determine this horizontal, determine the coupling from the horizontal displacement of the 2 components. And so we can get an accurate measurement. Now, another nice thing about this is that this experiment, we don't decouple C prime because we want to measure the coupling, right? And we also, so therefore the peak of this 4-dimensional peak actually split it twice. One is in nitrogen dimension by this 1 bond coupling, another CC coupling about 53 Hertz. So we measure the coupling twice, the same coupling, because one is from component splitted by this coupling, and the other one by that coupling. So we measure twice. And this is nice because we could actually use the 2 independent measurements in the same experiments to estimate, to evaluate how good the reconstruction is. And I'll get back to that later. And the same thing, the same coupling of this could also be measured twice. In this case, the small coupling of HNC prime is separated is not separated in HN dimension, but separated in the orthogonal C alpha dimension. As you see, this is 56 Hertz. So we use larger coupling to separate the small coupling, and it's very useful for measuring small couplings. A few details about that experiment. The time domain matrix, as you can see for 4D, it's huge, okay? And we only sample about 0.27%. And if you sample the whole data matrix, it probably takes a year or more to do. And acquisition time in indirect dimension is large. That's why we can get very high resolution. For the real-only spectrum, it's about 100 gigabytes. And if you let SMILE, if you give enough, like if you give SMILE unlimited memory, it can take up to about 500 gigabyte. And I realized at the time that not so many people can have access to a computer which has this large memory amount. So therefore, I programmed this so that the memory efficiency is high, and it only requires a minimum of about 40 gigabyte for this data set. So as I said, that the same coupling, 3-bond coupling of C prime H alpha for 3-bond is measured twice from the same data set. So we look at the correlation plot and we calculate the IMSD. It's 0.1 Hertz for about 3 Hertz coupling. So that's not bad. So to our own curiosity, we actually throw away 80% of the data and reconstruct it from 20% of whatever we randomly picked, and reconstruct it again and look at the correlation of IMSD. And the reason we want to do that is want to see if SMILE perform substantially worse when we have much sparser data. If it is, then the error should be much larger than what you can expect from the amount of input data. In this case, we only get 20% of data, so a factor of 5 reduction. And so if SMILE does not increase tremendously to the uncertainty because of poor reconstruction, then the IMSD should be proportional to square root of 5, which exactly is. Square root of 0.5 is about 0.225, okay? And therefore, we concluded that even at this sparsity level, the program performs well without contributing extra uncertainty to the measurement. The next example is that, again, Zhang Ho Li want to study how hydrophosphoronuclein interact with the membrane. In this case, he used a large vesicle, SUV, and you also can use LUV, small, small. Anyway, so the way he does that is to run an acetylation reaction by using this reagent in the presence of the lipids. And so as you can imagine, and using the side chain, lysine side chain, as you can imagine that if the part of protein where the lysine is, where 15 lysines, strongly interact with the lipids, then you can tell the reaction is slow because it's inside the lipids, right? Otherwise, the reaction is fast. So you could monitor the intensity change during the reaction to tell whether the interaction with the lipids is strong or weak. But here's the problem. If you just run HSQC of a acetylated lysine side chain, you get a very poor resolution. This is a regular HSQC. And the reason is that in the direct dimension of epsilon amide, side chain amide, there is J coupling to delta methylene proton. Okay, so that causes the peak to split, and therefore the resolution is poor in the direct dimension. In the indirect dimension for HSQC, we start from in phase nitrogen 15 magnetization, and then it evolves between in phase and antiphase, right? And that something called, when it's antiphase, there's something called a scalar relaxation of the second kind. So basically, the R2 relaxation of nitrogen, not only it's the R2 value relaxed not only according to its own R2, but also contributed by the R1 relaxation of the amides. And in this case, amide proton, in this case, it's the selective R1. So NOE effect, solvent exchange will broaden up the line shape of the indirect dimension. So recognizing the problem, here's what we do. In the indirect dimension, we get in-phase nitrogen and we apply CPD decoupling so that we keep the nitrogen magnetization in phase. And therefore, we remove the scalar relaxation of the second kind. In the direct dimension, we use a trick that we published earlier, this band selective homonuclide decoupling, so that the delta methylene coupling to epsilon side chain amide is suppressed. So by those tricks, we were able to get something very high resolution, almost completely resolve the 15 residues, and therefore we could Zhang Ho could really trace the intensity during the reaction very accurate. But then the question is, how do we assign it? Well, we use the toxic experiment, high resolution, okay? Using the tricks that we talked about in the previous slides. In the indirect dimension, we apply CPD. In the direct dimension, we apply the batch decoupling, and we do toxi so that the amide of the side chain connected to the other methylene and H-alpha proton as well. And this lysine side chain is long, okay? So we don't actually get transferred, the signal transferring from amide side chain amide to backbone amide. I'm not plotting them, it's somewhere sitting downfield in this area. But by looking at what the same aliphatic protons that correlated, connected to the side chain amide and the backbone amide, we were able to link assign the backbone amide with the side chain amide, and therefore we could assign that. And we got about 1.5% of sampling in about 30 hours. And again, if you don't do NUS, this cannot be done. We will not be able to get three-dimensional high resolution spectrum. Next example is that we have been doing this high pressure jump experiments to study protein folding. And at some point, we want to measure nitrogen-15 chemical shift at unfolded nitrogen-15 chemical shift of ubiquitin at 1 bar. And we use 2.5 kilobar to unfold the protein. And then we drop the pressure, and then we immediately want to measure the chemical shift of nitrogen and other nuclei as well, carbon-13 and proton. And later we measure also the NOEs and RDCs when ubiquitin is folded from unfolded high pressure unfolded state back to folded state at 1 bar. And so, so the reason we want to make those measurements is that we want to see what kind of structures when protein is unfolded towards the folding. So therefore, we better get a better idea about the protein folding. Now, the problem is this: when you do this, you need about 8 seconds of interscan delay, because it takes about that time to unfold the protein with high pressure. But folding is a lot faster. So what we do is that we wait for 8 seconds at a high pressure, and within a few milliseconds, we drop the pressure and protein started to unfold. But protein started to fold back. But before it has time to fold back, we call it the chemical shift. And that chemical shift is unfolded state at a 1 bar. And then we wait about 300 milliseconds, and then protein folded back, because folding is faster than unfolding. Then we read it out with HSQC, which is, we have already assigned those resonance. So basically, we link the chemical shift of these nuclei to the chemical shift of that we already know, and therefore we can assign them as well. And just to show you what kind of high pressure device it is, this is the first generation we called Icarus, because we use the static high pressure devices called a Daedalus, and Icarus in Greek mythology is a son of Daedalus. Okay, this is the first version built by Phil Enfenrod, a PI in the level of chemical physics. He's very good with this kind of things. He's the laser femtosecond laser guy. This is the first one. It's gigantic. It's not mobile. It's very hard to use. And you see the air is loading his sample right here. And later, he built a mobile version of the high pressure device. And you see those two valves, blue, are the high pressure valve and low pressure valve. If you want high pressure, you can code it in the pulse sequence, let it turn on the high pressure valve. And if you want a low pressure, you can turn it on valve, the low pressure valve in milliseconds. And these are the two valves for the mobile one. The postdoc Ashley Barnes is trying to load that to my 900 megahertz magnet. Okay, so next example, Ashley, the one that you see in the previous slides, was interested in studying the single axis helix domain of myosin. It's protein that involved in the muscle. The problem is that this protein has high lipid of 3 residues. 72% of SAW is E, K, or R. As a result, you see that the chemical shift dispersion is very bad. Relative to normal protein, like normal folded protein like ubiquitin, you really only get about 3 to 4 ppm for majority of the peaks. And therefore, you need something really high resolution, and also the traditional backbone assignment strategy fail, because when you look at E, there's so many E's over there, and the H alpha is so similar that you really couldn't take the walk between the sequential, HN and sequential H alpha or H beta. So this doesn't work. we rely on this noisy-based approach to do that. So basically, for helix, the two sequential amide are very close in space. Therefore, we can mount a high-resolution 4D nosy, and we can take the walk. For example, here, if you go to, this is basically, it's really F4, F3, not F1, F2. If you go there, and then you go to one peak and see, hey, you get an E34, and then you go to this peak, go to that plane, correspond to points, the coordinates right like here, then you get an E35, and therefore you get a sequential connectivity, and even some long, three bond, II plus 3 peaks also seen. So by doing this, you get all the sequential connectivity, and in the end, with the help of HNCACB, you actually he was able to completely assign this. And there's some nice story, after assignment, we'll get some nice story about this, this protein, and particularly some of the RDC work that I think is very interesting. If you want to see, read this paper that we published last year. Next example, I like to talk about another piece of work that published last year, is that usually, particularly for Bruker, if you use the Bruker standard NUS experiment, it's we assume that the sample is stable, okay? Because the sampling schedule is randomized. I'm not talking about the random sampling, like pick up the sampling point randomly. Instead, I'm talking about the order of the time points, and it's randomized, okay? And that's a problem for traditional, usual way of doing non-uniform sampling. And we see this problem when we try to study A beta, amyloid beta, 42 residues, A beta 42. And this is aggregation kinetics. You see that it can be fitted to by exponential decay with time constant of roughly 5 hours and 33 hours, okay? So in less than 2 days, 80% of the sample is gone, okay? And the problem of, this kind of signal decay or sample degradation cause a big problem in NUS if you don't do something special. Let me illustrate the problem by simulation. A 1D simulation on resonance, 1D, one peak on resonance, okay? So you just simulate it, and then imaginary, if it's on resonance, is 0, of course. So it's just the real part, which is smooth decay, and this is R2 decay. And if you want to simulate, if you want to Fourier transform, you get something like this, very nice peak, all right? Now, you try to make the sample decay. It's hypothetical, of course, because within about 100 milliseconds, nothing is going to decay that fast, right? But let's see, within 100 milliseconds, it decays a little bit. You see that it goes lower than this by the end, because this decay is R2 plus whatever the sample decay, right? So you get a peak, you get a little bit broader peak and a little weaker, not as sharp, because you have actual loss because of sample degradation. Now, let's think about if you randomize the order of the sampling, meaning that, let's see, early data points is acquired at a later time, or later data points acquired earlier. As a result, because you randomize the order of the sampling, you actually get a very noisy time domain signal. And Fourier transform that, of course, you get a very bad noise-like, artifacts. And that's because the intensity is no longer a smooth decay, but randomly oscillating, okay? And in the end, you not only get a weaker signal than this, you also get a very noise data. But the good news is that the line should be as sharp, almost as sharp as the case without decay. So how do we solve this kind of problem? Well, in the literature, people already proposed something. This is a group from Australia, Mobley group. They proposed that let's just run multi-sample, low concentration, okay? Because for A beta, a high concentration decay faster. The lower, the slower. And in our case, I didn't point it out, we also use a high pressure, 3 kilobar. High pressure helps slow down the degradation, aggregation process. So Mobley group basically saying that, okay, let's do a lot of experiments with a lot of samples in low concentration, and later on we just pull the sample together, we'll get a nice data. But sometimes, like we want to do noisy experiment, we want to use high concentration so that we see some weak peaks, right? So here's what we propose to do for we propose another two approach. One is that if we know the degradation or aggregation kinetics, we could actually apply a correction to each FID, because we know when each FID is collected, we know how many percent is signal decayed, because we know the kinetics. Therefore, we can scale up the signal so that the signal in the data has no decay because of sample degradation. However, the problem is that the noise is also scaled up, okay? And I'll show you a spectrum how this approach works later. Another thing that actually Adibax proposed to do is to just order the sampling schedule. And we did a simulation to evaluate what kind of ordering scheme works the best. So we have 6 simulations here. This one is random, meaning that there's no ordering. T1 and T2, by talking about ordering, really meaning that the 2-column list, and it's random, okay? The order is random. You could have larger T2, T1 in the beginning and small T1, T2 in the end. These T1, T2, I meant it's not T2 relaxation, of course. It's the time points in the 2 indirect dimension. I assume it's a 3-dimensional experiment. And we only sample one plane of the 3-dimensional. So this is a reference, and every other plane is plotted at the same time, the same contour level. So if we order according to T1 plus T2, we get something like that. And we have other ordering scheme. For example, here is really, we order according to the normalized length of the T1, T2. And this is a traditional way, as if you run the experiment traditionally, meaning that you collect the T2 point first, every T2 point for the first T1, which is 0, then you move on to collect every T2 with T1 equals 1, and they keep it going on and on. It looks nice. The problem is that the impact of sample decay is completely on the T1 dimension, because it's the T1 data. T2 data is collected relatively shortly, within a short amount of time. But the T1 is really the first T1 collected in the beginning of the experiment, the last T1 collected in the end of the experiment. So signal decays a lot, and therefore you get a much broader peak. So this is not recommended. It's too broad. So all the other 4 is really acceptable, and they're very close, but we evaluated the overall performance, and we set on this approach that gives slightly a better high signal to noise, and also the line shape looks a little bit closer to Lorentzian, and the noise level, artifact level is slightly lower as well. And these are really just the cross section. For example, cross section based on the T2 without transforming T2, this dimension, sorry, without fully transformed T2, but fully transformed both T1 and T3. And so you see that when it's random, you see the time domain signal is very noisy. All the other signal, all the other ordering scheme works well, but some of it clearly you see deviated from Lorentzian because it's no longer exponential. And this is along the T2 dimension, the T1 dimension, and same thing. The reference is noisy. So we set on this, and we did a 2 experiment, interleaved, okay? One is that, by the way, we actually just do 1 experiment, but use 2 sampling schedule interleaved together, okay? One sampling schedule has random order. The other one has been ordered based on the normalized length that I discussed in previous slides. You can tell when you don't order that, you see this kind of noise, sampling artifacts, but it's not, it's really T1 noise. That there's no way, no program could actually remove that. And the ordered spectrum gives you better, much lower artifact level. They are plotted on the same relative, I think the same, because signal to noise, relative to the intensity is the same noise level. But the peak, it's hard to see from here. Maybe I'll go to the next slides. The third one, the third spectrum is really the same data set from the first one, but we do the intensity signal upscaling to account for the sample loss during the experiment. You get a cleaner data relative to that, but you get a little bit weaker signal because the noise level is also scaled up, and it's better seen from the cross section that taken from the previous slides for two residues, two cross section, and along this vertical dimension. Okay, so basically we take two vertical slice from those three spectrum. Okay, so when it's ordered, you see that you see every weak peak. When it's random, you really don't see a lot of peaks. And when you do upscaling, you recover a lot of peaks more, but it's just not as good as this. However, the line is sharper, okay? And so basically this time ordering of the sampling schedule is to trade the resolution slightly for better signal to noise ratio. The last example, what time is it now? It's about 11, we have time. The last experiment is the last example. I want to show you some measurement about RDCs using this thing called RT, published a long time ago. It's called the RT. I think it stands for amide RDC Chauzy spectroscopy. So you can measure RDC with using a lot of methods, IPAT, or even from peak difference between Chauzy and HSQC for large protein. But for large protein, the best method in our hand is really Chauzy based. So basically, we run two spectrum, all Chauzy based. So really, we measure the RDC from the narrowest components, but we make sure that one spectrum, the intensity is modulated by this sine function, okay? Those half of the t. And the other spectrum is modulated by the full t. This is the half t. Now, if we choose set t to be 1 over j when d is close to 0, or when you measure the isotropic sample, this so-called attenuated spectrum hits the null. As you can see, those two peaks, really you don't see anything. It hits the null because this is sine 180. Therefore, this is sine 90. You get the reference spectrum, okay? And when D is not 0, then it's either larger or smaller. You get either positive or negative peak. But the reference, you always get nice positive peak. And by taking ratio between the two spectrum, the peak ratio, you can figure out what is the J plus D, or what is the J if it's an isotropic sample. And with that, we were able to measure something very large, is about a 68 KD, the RDCs, and it fits pretty well. And here's the thing that I want to point it out. As you can imagine, if you do this, the reason we do 3D is that 2D is too clouded. You cannot separate all the peaks in Chauzy. And therefore, we get another CO dimension to separate this. And therefore, we can get almost every peak. If you reconstruct it with an algorithm that if you have 50% sampling, for example, your reconstruct signal will be twice stronger than the intensity captured in the measured data, because half data is not measured, right? So you add another half of data, the measured data, the reconstruct data. If you add it into the spectrum and you reconstruct the whole spectrum, peak height is higher. But for the peaks that are missing, there's nothing to be reconstructed. So it missed that scaling effect of 2. And therefore the ratio is not going to be accurate. And therefore your measurement will be off by a lot. With this kind of problem in mind during the development, we really try to make sure that SMILE to keep the intensity that captured in your data, okay? Try to faithfully, of course, and never be perfect. So whatever captured in the data, in the end, SMILE, make sure that the spectrum, the intensity is close to that. And therefore, if you even miss a peak in this attenuated one, because the reference data is not off by a lot, and therefore the ratio is still accurate, and you get an RDCs that gives you a reasonable Q factor. I think this is about it for this morning session, and a bit of summary. I hope you agree by this point that you're convinced that with NUS, doing 4-dimensional NMR, you are no longer limited by resolution. You pretty much can reach the natural line width if you want, okay? And of course, it's limited by natural line width. You cannot do better than that. But in the past, if you do 4D, you're limited by the amount of time you can collect the data, and therefore you have to sacrifice. You can never reach even close to a natural line width for 4D, even for something large. But with the NUS, you're no longer limited by that. And also, like I just pointed out, that the SMILE try to maintain the peak intensity that's in your signal. So if you have a data set that has low signal to noise, you're gonna see a low signal to noise reconstructed spectrum, okay? Instead of something, if you have 10%, you may get 10 times boost in the spectrum, and that boost is artificial and should not be considered as a real signal to noise. Well, you never have this problem if you deal with SMILE reconstruct the spectrum. Since we have time, I think is that actually we are over, right? Are we?
No, yeah, Jim, but you're fine. You're fine.
6 minutes over. So I don't know if people okay with delay the break time. We can have a few questions. Otherwise, we have a break, and I'll see you at 11:15. That I'll talk to you about basically the NMR experiments and some of the very practical hands-on stuff, so that as an introduction to my demo.
Jinfa, there were 1 or 2 questions that were posted in the chat window.
Oh, really? I'm really sorry.
Maybe we can address those, and then we'll be able to move on to our break.
The chat, yes, I'm very sorry. I didn't see it.
No, that's quite all right. I kept an eye on it, and you were towards the end of your talk.
So from Max, have you ever used iterative simulation similar to approach estimate R2 to estimate a small J value as alternative to E cozy? Actually, we did not. For J value, no, we never did that. But it's something that we could do, right? Very easily. You could simulate data set with certain J, and then you could make a measurement. But I don't understand why do we need to do iteratively for that? Oh, do you mean, Max, that you wanna iteratively figure out what's the J value in the line shape? Because some low resolution, for example, if you acquire 100 millisecond in the direct MI proton dimension, the HNH alpha coupling is not resolved, and therefore it's in the data set, and therefore he probably is right that we could iteratively simulate J and figured out to better simulate the reconstructed data. No, we don't do that. I suspect that the benefit probably is not significant, because even if it's not resolved, even if it's deviated from Lorentzian line shape, if two peaks are close but not resolved, but about to resolve, you're right that this is not Lorentzian, and it's better if we know the J and simulate the J. But the program as it is does not do that. Also, I actually allow you to enter, provides a rough consensus J value to the reconstruction. So I really don't understand why this. So I'm sorry, I don't really truly understand the question, whether this is about the measurement of J coupling or it's about the reconstruction, because you also.
So GenFi would be both. So one, potentially it would be an alternative to an eCOSY experiment if you didn't happen to have run one to estimate these, some of the smaller J values.
Mm-hmm.
But as you say, it could also be used to improve, potentially used to improve a reconstruction when you have unresolved J values.
Yes. It's possible. We haven't done it. Instead, we use something simpler that is allows you to enter a J coupling into the reconstruction in different dimension by XJ, YJ, ZJ, something like that in Hertz, I believe. For the measurement, I don't know if this could be done with the like more accurately from the reconstruction itself. I'll think about it. We can discuss this at the end of this, or at the end of the day, or we can exchange by email. Okay. I'm sorry, I really don't have good answers at this point, because I agree. I admit that I never think about this. Okay, Max. Next, if the decay rate is now, would it be easier simply to scale the acquired data points accordingly? Yes, actually, if decay is now, you don't really need to do that. For example, constant time dimension, it has no decay, and therefore I don't need to do simulation even. But if you doing non-constant time and you know the decay, yes, you are right. It's better to enter the decay rate to it. But unfortunately, at this point, the program does not allow you to provide that. And if you have application for this in this regard, I can work with you and try to get something like that to have a fixed decay rate, and hopefully it's better. Okay. So email me if you want something like this to be developed. And thanks for the question. Yeah, that's a good point. Next question is, if it's not approximate, you could iteratively approximate it to deconvolute that decay in a maximum likelihood fashion. Possible, yes. Again, I never thought about this, and I can't comment on it right now. Okay, so if you have more thoughts that could help make SMILE works better, please write to me, and I'll appreciate it. Next question was SMILE algorithm in NMR pipe. Can we achieve effect similar to signal upscaling for random order by S? Yes, I thought about that and was discouraged by my boss at Bax. He thinks that a lot of people simply will get confused. Okay, number one. Number two, it also needs a good, like in my NOSI data, I did it by I monitor the decay by actually insert the first increment FID every 1 hour. So we measure the first, when signal is nice and strong, we measure the first increment many times, okay? Once every hour. So yes, the data has the information about the decay, and in principle, SMILE could use that to apply the scaling factor. to it during the reconstruction. But as of now, no, we don't do that. Instead, I wrote a C program, I believe, just to do the scaling once. Okay, so basically I manually extract those data points that I put it in, I spiked it in, and then figure out the decay, and then manually apply the correction before the reconstruction. So you either do ordering like this, or you monitor this and then apply the scaling, like I say, after data is ready, but before the reconstruction. It's a good point. It's something that I was interested, but my boss didn't think that it's very, it's worth the time. So, I mean, this doesn't mean much. I could still do it if you're interested. If this works better for you than doing a time ordering. So let me know. Okay. Any other questions?
Jinfa, I think this will be a good time to take our break.